Hi everyone, I'm Jay, and today I'll be presenting our paper, Appraisal Theory Informed Emotion Prediction. In this paper, we ask whether large language models can reason why emotions change in conversations, not just label what emotion is present. This is a joint work done with Xiaowei Wang, myself, Ray Mao, Wandeep Kaur, Sabrina Thion, and Eric Cambria. This paper has been accepted for LREC 2026. So what's the problem? Existing emotion recognition models classify each utterance's emotion in isolation. They tell you what emotion is present, but not why it's there. There's been some recent work on causal or appraisal-based approaches, like CAPE, but it's fragmented. There's no systematic test of whether these models can reason the way humans actually do. And critically, none of the approaches capture the key psychological driver behind emotional shifts, the gap between what a speaker expects to happen and what actually happens. Conversational emotion is dynamic. People form expectations, check whether they are confirmed or violated, and update how they feel accordingly. That's what we wanted to test. This is grounded in Scherer's appraisal theory. The core idea is that emotional reactions aren't a direct outcome of events. They come from how a person cognitively evaluates an event against their goals, expectations, and norms. We formalize this as a four-step chain. First, the speaker forms an expectation about what should happen next. Then, an event occurs, something is said or done. That outcome gets compared against the expectation. Is it a match or a violation? And finally, the emotional state updates based on that comparison. This is exactly what we mean by emotion prediction as opposed to standard emotion recognition. Instead of just classifying what emotion is present in an utterance, the model is to predict how the emotional state evolves by reasoning through this cognitive chain, step by step. From this, we derived 4 research questions. Research question 1. Does explicitly indicating expectations improve prediction accuracy? Question 2. Does indicating violations improve detection of emotional shifts? Question 3. Does combining expectation and violation give a synergistic boost beyond either alone? And the last question. Are certain emotional transitions more sensitive to these appraisal mechanisms than others? Each comes with a corresponding hypothesis, which I'll come back to in the results. To test this, we designed 6 prompt tasks that simulate the appraisal chain. Q1 infers the speaker's expectation. Q2 through Q5 generate the speaker's next line under 4 different cognitive conditions: baseline with no cue, expectation only, violation only, and both combined. All using identical decoding parameters, so we isolate just the effect of the cue itself. Finally, Q6 is an independent evaluator that labels the emotion each generated line expresses. Here's a quick example from daily dialogue dataset. When primed with expectation, the model generates, "Oh, I see. I was expecting you might have gone to one of those fast food places." And this correctly predicts surprise, matching the ground truth. Here, we used 4 standard ERC corpora: daily dialogue, Emory NLP, IMOCAP, and MELD, but filtered them aggressively. We only kept dialogues and speakers with genuine emotional dynamism. At least 4 emotions per dialogue, at least 2 shifts per speaker, then labeled them using an appraisal-driven detection algorithm. The appraisal-driven rate changes from about 12.6% in IMOCAP up to 50.6% in Emory NLP. The key takeaway here is that appraisal-driven emotion changes dominate in every corpus. Most shifts follow what another speaker says, not internal self-reflection. Our experimental setup is large scale, 8 generator models like GPT 3.5 Turbo, GPT-4, Gemini 1.5 and 2.5 Pro, DeepSeek, and Chuan variants. With that, they are crossed with 4 evaluator models, 4 datasets, and 4 prompt conditions. That's 128 total configurations, each evaluated on both label accuracy and transition dynamics, with temperature fixed at 0.7 to keep things comparable. Now the results. The headline finding is expectation helps, violation alone hurts. Across all 128 configurations, Q3, the expectation primed condition, beats the baseline 76.6% of the time. But Q4, the violation only condition, actually fell below baseline 79.7% of the time. And combining both, Q5 only beat expectation alone in 20.3% of configs. So there's no real synergy from stacking the queues together. Breaking this down further, GPT-4o was the top performer on daily dialogue and Emery NLP, showing strong robustness across corpora. Gemini 2.5 Pro and GPT 3.5 Turbo were roughly comparable mid-tier performers, while smaller open models like Chuan and DeepSeek were weaker and less consistent in picking up on expectation cues. By dataset, iMoCap had the highest accuracy. It has rich cues that are easier to pick up, whereas MELD was hardest due to ambiguous labels. We also looked at whether models can detect the direction of emotional shifts using Cohen's K. Across all datasets and generators, kappa falls between 0.25 and 0.36. Small to moderate agreement, but statistically significant beyond chance for every single configuration. That said, there is a clear stability bias on Emery NLP. For example, GPT-4o massively overpredicts no-change transitions while flattening positive emotions towards neutral. So models can tell direction is happening, but they lean heavily towards predicting stability. Pulling this together, hypothesis 1 is confirmed. Explicit expectation cues generally improve accuracy, up to 2.4% on MELD. Hypothesis 2 is rejected. Violation cues alone actually mislead the model and hurt performance. Hypothesis 3 is also rejected. There is no consistent synergy from combining both cues. They may or may not hurt the performance. And hypothesis 4 is supported. LLMs do infer shift direction of chance, but they overpredict stability and underdetect fine-grained shifts. So, the big picture takeaway is that emotion prediction reframes emotion recognition as a reasoning problem, not just a labeling problem. This matters for building interpretable, effective computing systems, for mental health, and for empathetic dialogue systems. And it also gives us a cognitively grounded benchmark for testing human-like reasoning in LLMs more broadly. Going forward, an open question is how to get models to model fine-grained shifts, not just overall stability. Thanks for watching.